Speeding is defined as exceeding posted speed limits or traveling too fast for road conditions. Drivers may speed based on peer actions, a desire to save time, or an overestimation of driving ability. Speeding is known to pose significant risks for all road users by increasing the frequency and severity of crashes. However, it is still common for drivers to exceed posted speed limits, and the consequences cannot be overlooked. From 2017 to 2021, total annual traffic fatalities have been increasing in the U.S. In 2021 alone, speeding-related fatalities made up over 25% of total fatalities. Why does speed matter? As drivers increase their speed, their reaction and stopping distance also increases, which translates to higher collision risk. Crashes at higher speeds also result in more severe collisions because the subject vehicle has a larger kinetic energy. Today, 33 states have max speed limits of 70 miles per hour or above, and 8 states have roadways with 80 or 85 mile per hour limits. Though speed management is recognized as a critical strategy to reduce crashes, speed limit hikes have still been discussed in multiple states within the last 2 years. With technological advancements, there are now also opportunities for in-vehicle technologies to serve as scalable safety interventions. Examples include intelligent speed assistance, or ISA, which provides feedback to drivers if they're speeding, and automatic emergency braking, or AEB, which applies brakes if a vehicle or pedestrian is detected in close proximity. Significant progress has been made in enhancing safety standards. ISA has been mandated in Europe for all new cars sold from July 2024 onwards. More recently, AEB has been mandated as a requirement in the US on all passenger cars and light trucks by September 2029. However, there are some drawbacks inherent to driver assistance technologies. For ISA, the compliance rate could vary and drivers might not actually slow down. For AEB, only emergency close call accidents may be prevented. At the same time, there are no guarantees and speeding-related risk remains. A potential alternative to driver assist could be formal speed limiters, equivalent to 100% compliance with ISAs, where vehicles are capped at the maximum posted speed limit. This idea has been considered specifically in the trucking industry, with opponents claiming that this would lead to more congestion and traffic jams. To explore the effects of speed limiters, I used microsimulation to model a single-lane scenario. I tested 3 different maximum speeds, including 45, 65, and 85 miles per hour. The vehicles are simulated using a car-following model. The model determines the acceleration of the ego vehicle based on its relationship with its leading vehicle. Depending on the spacing and velocity of the vehicles, an appropriate acceleration can be determined at every time step. A specific car-following model called the Intelligent Driver Model, or IDM, was used. The acceleration function for the IDM depends on the relationships between the current and desired spacing of the vehicles and the current and desired velocity of the vehicle. At a high level, the ego vehicle will accelerate to meet the desired velocity if there is adequate space to do so, and will decelerate to meet the desired spacing if it is not met. The IDM parameters have practical interpretations related to driver behaviors. For example, the time gap parameter T relates to the driver reaction time, which could be smaller to represent aggressive behavior or larger to represent a sluggish driver. These parameters were tuned to allow for max velocities to be reached in each simulation. In order to evaluate safety, surrogate safety measures were used, which are proxy indicators that estimate collision risk. The first one is time to collision, or TTC. TTC measures the time it takes for 2 vehicles to crash if they maintain their current speed and path. TTC can only be calculated if the ego vehicle is driving faster than the leading vehicle. Another surrogate safety measure used in this study is deceleration required to avoid collision, or DRAC. DRAC measures the deceleration needed for the ego vehicle to decelerate to avoid a rear-end collision with the leading vehicle. In general, a higher collision risk can be interpreted by a lower TTC and higher DRAC. We would expect to observe measures indicative of higher risk as the maximum velocity threshold increases. This graph shows the distribution of TTC values across the 3 max velocity thresholds tested. As expected, TTC is lower when the max speed is higher, corresponding to higher risk. As the max velocity decreases, the distributions are also wider and outcomes are more variable towards higher TTC values. The median TTC values for both 65 and 85 mile per hour limits were found to be over 90% smaller than for 45 miles per hour. The DRAC distributions also align with our expectations, with lower max speeds experiencing smaller DRAC values. What about the impacts of speed limiters on congestion? We can understand congestion by plotting fundamental diagrams where the y-axis is the traffic flow in vehicles per second and the x-axis is the density in vehicles per meter. The critical density Kc is when max flow is experienced and free flow conditions end, while the jam density Kjam is the density at which traffic flow stops completely. From these simulations, the critical density was found to be the highest for lower max speeds. This makes sense as slower vehicles can accommodate smaller gaps, resulting in a higher density than those driving at higher speeds. Interestingly, the opposite trend was observed for the jam density, where Kjam was lower for lower speeds. This could be influenced by the minimum spacing and time gap constraint, which was held constant across all simulations.